Fernando is a professor at the Paris Cergy University. But before that, he's have been to Dresden, and he did a PhD in the Max Planck in the physical complex system in Dresden. And then he got a position in South France. And now he's a professor in Paris Cergy, and his research is focusing on statistical physics of a living system. So it's a broad field, very broad field, and he had been working on very diverse topics. And I think he's theoretical physicist by training, but he showed that he's also have a very few inches on connecting theory with experimental. So thank you, Fernando, for coming.
So, yes, thank you for the introduction. Okay. Press OK, please. Yeah, thank you.
All right. So to track time, I don't know. So thank you for the invitation. You have fantastic location really here. So all right. So all right. So let me start by telling you a bit what we do in Searching. So what we do is basically we look at different biological systems across scales that goes from bacteria to sheep. And basically what we do is we try to propose equation of motions or behavioral rules for the individuals. And we try to see whether these behavioral rules that our equation of motions for the individuals account for the macroscopic behavior that we observe when we put a collection of these individuals. So basically what we try to do is to connect a microscopic description with a macroscopic description, right? So if you want to say it a bit more mathematical way, so we start with the Lagrangian approach and we go to an Eulerian approach. So that would be in terms of typically PDEs and so on. And this is a kind of HM-based models. And of course, you can go, the arrow goes in this way. If you try to go the other way, you have many options in general, right? So anyway, so this is typically the approach that we take. So why we would be interested in, okay, so, and to introduce a bit the kind of things that we do, this is what we do in terms of applications, but in general, what we try to do is to develop a kind of statistical physics or a theoretical framework to understand biological systems in general collections of either from microorganisms to animal systems. So, and basically this is out of equilibrium systems. And then what we try to do is basically to see how we should expand and enlarge the typical approach of statistical mechanics from physics to something that is out of equilibrium as these biological systems. Okay, so the main reason why, I mean, let's say if you are a biologist, you may wonder why we need mathematical models. And I think at least the kind of things that we have been doing can be useful for two things. One is one can use this approach to test biological hypotheses. And then basically what you can do is what is the second point, that is you can have an idea of how things work. You know, you put it in an idealized kind of framework, the model, and then you test whether that brings, I mean, provides the kind of output that you were expecting. So you can test hypotheses in that way. And then, I mean, what the ultimate goal for us, as trying to describe the system, is to get rid of many of the details that will be required to fit the experimental data to get what is basically the self-organizing principle, the minimal model that will describe what we are observing, which might not, I mean, if once you try removing details, you will get something that, of course, is not as accurate that you will get, I mean, if you are trying to be quantitative as when you put many details in there. But then you can identify what is the essential mechanism. So what here I'm calling the organizing principle of self-organizing principles. Okay, so, but which kind of model should we use in this kind of framework? And this is what I will basically try to convince you that what we are developing is quite useful and can be used in biological systems, but perhaps even beyond. And this is the following. So the idea is to think that we have a collection of individuals, and these individuals are not just, a physical particle. It's not a spin or a gas particle moving around, but has, the peculiar thing of our particles or units is going to be that they have what here I'm calling a mini brain, an internal control system. And this internal control system here, in what I'm going to show you, is going to be a Markov chain, could be something else. But here in the examples I'm going to show you is a Markov chain. And that Markov chain will tell you which equation of motion for controlling the behavior of this unit in physical space the individual has to use, right? So this mini brain is basically making a decision on how to behave in physical space for these individuals. And once they are in physical space, then we will be using kind of a standard physical approach. So let me explain a bit more. So suppose, this is kind of we developed for understanding things that are moving in space. Of course, you can try to go and generalize this. So imagine that you have here, I'm going to think about what happens with one individual. So you have this individual over here that performed this trajectory. Of course, it's very idealized, and you see that this individual is behaving, in three different ways, and at some point is moving in space, performing a kind of spiral pattern, then a kind of zigzag, and then that square blue thing at the end. So let's imagine that the trajectory is super long, and then alternates between these different patterns. So now what I'm going to tell you is how you can look at the data in such a way that you can start building the kind of approach that I try to convince you that is useful. First, what you do is, for example, you identify from your trajectory each of these patterns, and you compute for how long it is in this spiral kind of pattern. The motion is of this kind. So now you have a distribution of time because the trajectory goes into the spiral, that's something else again, and the spiral and so on. You compute the distribution of time. Your unit or this particle individual is in this spiral kind of pattern. Then you compute the same for the zigzag and the other pattern. So every pattern that you have, you compute the statistic of these times. This, you will use it to build this mini brain in the following way. So the distribution that you will see will tell you the minimum number of nodes that you should be using to represent, for example, the spiral. Here I need 4. To represent the zigzag, I need at least 4. Each of them, the color is telling you which pattern it is, which means that if I'm in a black node in the internal control system, this mini brain, I have to use the equation of motion 1. If I'm in one of these red guys, red nodes, I have to use equation of motion 2, and so on, right? So basically, depending where I am in this Markov chain, I have to use a different equation of motion. That's the idea. And this equation of, each one of them could be extremely different from each other, right? The only thing is the equation of motion 1. Oh my God.
Double click the slide, the screen, please.
What I have done,
double click the screen. On the slide. Slowly. Somewhere in between.
Okay, so
can I ask a quick question now? We have
Yeah.
a break anyway. So are these Markov chains using the same internal states for every behavior, or are they different Markov chains?
no, it's the same Markov chain. You have, let's say, a kind of click, whatever you want to call it. You have a set of them wired in a particular way. When you leave from one of these and you go to some of another, you have the same Markov chain. You paint in different colors, let's say the nodes, to identify which equation of motion.
But if black nodes and the red nodes are not the same nodes, they are really different nodes in the same chain.
But that is for us only.
Yeah, but I mean to interpret.
Well, the transition rates.
Because there are, of course, as Sarah says, there are transitions between those. Right?
Yes.
And are we really talking about going from one particular state black to a particular state red? Or is
this one could in eventually you may distinguish what happens between the three of them, or you may not, because that depends whether what you want to do. So if this is your brain, you may be thinking different things at the moment, but you are not telling me everything that you are thinking of, right? That basically, but if you may manifest whatever you are thinking, and then I may know in which node you are. So you get the point? So I will.
Maybe I think to clarify the question, the transition matrix here is 8 by 8.
The transition matrix.
Yeah, the matrix of transition. Maybe that's a question. Yeah. Is it an 8 times 8 transition matrix?
Yes, there is a transition between all of them. So we will have all the rates of, and this is.
Red and green.
Yes, there is rates between everybody.
Okay, then that was actually very good.
Yes.
This trajectory, is it independent, so there's no other agents around?
Yes, there's agents around, there is the environment, there is everything that you want.
The extraction of these three kind of
That's-
some space model or something.
Let me go to the next slide. I think we
Okay.
clarifies a few things. I mean, the entire talk is to explain this.
Okay.
So, and I'm giving you the overall picture. Yes,
So one more question about that.
yeah.
So you start with identifying these three different phases with their three associated statistics.
Yeah.
Does that mean that you infer these transition rates of this one matrix from these three different statistical distributions?
Yes,
Okay.
but you will see how.
Okay.
So let me move forward, because I'm giving you the overall picture, and then I mean the entire talk is to explain this in detail. So yes, you may get some details are kind of, I give you the overall, I mean, trying to give you the picture, and then I'm going to the details, right? So this comes into the question whether they are alone or not. So basically, since we have this kind of description, we have two types of interactions. First, since these guys are moving in physical space, you will have forces toward everything. I mean, you will have physics. The standard physics is in here. So this is physical space. Then what you have is transitions and things that occur within the Markov chain, that is the internal state of these agents. Now, in terms of the mode, you can choose whether these individuals are able to access the internal state of other agents or not, which I think is more realistic to assume that what they can perceive of the neighbors is whatever is happening in physical space, right? So I may know what you are telling me, not necessarily what you are thinking. I may realize what is happening with you because of your reaction, your body language, but not necessarily, but I don't know genuinely what is happening inside your brain. So now said that, the transition rates depend on whatever happens around you, right? Transition rates will depend on your environment. Your environment includes the environment itself and the neighbors and the state of the neighbors. Typically, the state of the neighbors is not going to be that you have access. I mean, our individual not necessarily is going to have access to the internal state of the neighbors. This kind of whatever happens in the Markov chain of the neighbor, but a physical manifestation from the neighbor, where it is located, whether it's shouting or moving, running, staying, so on, right? So we have this, we have then a dynamics in internal space, a dynamic in physical space, and of course, strong coupling between these two spaces.
May I ask about that?
Yes.
Also going back to the transition rates in the Markov chain, are they dependent on X? Is there
On X, yes, depend on everything. Yes.
And you said they change as the system evolves? depending on the neighbor.
They can also, yes, and they can even involve the equation that regulates the transition rates. So they may be adapted. So, okay.
And they're still Markovian. It's kind of.
Yeah, I mean, now is the thing. If there is no interaction with the neighbors, what in general, what you can do is you can see that what you can represent the things the following way. So you can write, I mean, this is, you can, let's say, this is a very simple example. So that there is a particle that depends on internal state Q is changing the velocity of the agent. This S, in fact, also could be regulated by is regulated by the Markov chain, the noise also, whatever you want here. Now, since there is no interaction with the others, typically you can write this in this way, which allows you basically, this is the probability of finding my particle in a given position in physical space at, say, position X at time T with internal state M, I mean, in one of these nodes. So now what I can exploit is the dynamics of this Q, the transitions within that Markov chain. And then basically what you can do is an adiabatic elimination of this. So assuming that this is fast, let's say that you do that. And then basically what you can do is you can build an effective equation for the dynamics in a space. And this is going to allow you, for example, to get what is the effective diffusion coefficient, effective velocity of the agents, and so on, forgetting about whatever was happening in the mini brain, right? So you can do a bit of math with that. If you are interested, you can take a look to these different papers. And in this case, they are interacting with the environment, but not with the other agents. So I may look whatever happens if I have food, if I have a chemical gradient or something around, but not with the others. Because when you get the interaction with the other, that gets nonlinear, and these beautiful things that you can do whenever there is no interaction with others is gone. So and it's no longer easy to get closer expressions for getting the effective diffusion coefficient and so on. So
Blue box, is it sort of a Fokker-Planck type of thing, or am I not?
if you want, I mean, you can call it a forward homolog equation with, I mean, transition, right? I mean, champs or whatever you want. Yes, it's kind of things. So you have a mixture of, how you would call it, a master equation, but you have transport, because that's also what is happening in continuous space. So you mix up these things. Right? Yes.
Yeah, another question is, you said something about time scales, fast and slow. So do you assume that everything is fast in the mini brain?
No, not necessarily, because what basically what you can be doing is the center manifold reduction, right? And that allows you, basically what you need is eigenvalues. Some eigenvalues are 0, those are the slow things, and the others are non-zero. That's the only thing that you need. You don't necessarily require this thing to be slow, but when it's slow, it's way easier to understand what is going on with the math.
But do you, okay, so but then you have a kind of a separation of time scales somewhere. I mean, the eigenvalue.
It might be there, or might.
But you're not assuming.
Yes, I mean, I'm not assuming that one thing is faster than the other. When you do, things simplify, certainly.
Sure. Okay.
I mean, all right. So, yeah, another question.
So
Yes.
is there any limit on the number of states that you have in your market chain, or the number of
No,
agents you
you can have as many as you want.
But then
Finite
there's
also.
a finite number of agents that you can observe. So this equation, you've got some observations per state. If you only have one agent in one state.
You will see, because I will start with bacteria, which is going to be, we will be looking at individuals, then we will be looking at sheep. So basically, this is how we apply this framework to understand real data. And I will go with first bacteria and then sheep. Okay.
Can I have a question about the previous slide before
Yes.
you go into the experiment? So in the previous slide, as you said, you have this time scale separation, and basically you take into account the effect of the mini brain as some effective diffusion constant, as you said. So this means I only see one way influence, like from the mini brain to the movement dynamic, to that interaction dynamic in the spatial location. but I don't see how the interaction in the physical space affect the mini brain dynamic. So does this mean that the mini brain is just a
No, because it will do. I mean, one example is, for example, in this paper in here, we show how with only 2 states without memory, I mean, having this Markov chain, you can do chemotaxis, where in general you will need to get basically a memory kernel. So basically, yes, it will, as you constrain the thing, will depend. In this case, it depends on how you react to the chemical gradient that you have, you are sensing. I mean,
but
with the
do you have
chemical
any-
concentration, in fact.
Do you have any equation of motion for Q? Like shortly speaking, I see the equation of motion for X, and X is the state variable for interaction in the physical space. Do you have an equation for Q?
Yes, of course. Well, I mean, the equation for Q is the Markov chain.
But then how that Markov chain
Is
get
where are you
modified?
located in that Markov chain?
But then how this Markov chain get modified after the interaction in the physical space?
I mean, that is going to depend on how is the equation for the rates. And in this example, I'm going to show you that is going to be a fixed equation,
Mhm.
but then you can also assume that the coefficients of the functional form that, I mean, is defined the rates also has an equation in itself, this coefficient, which means that may be evolving over time.
M refers to different states of Q or?
I mean, here, this Q is, I mean, it's a matter of notation, these are the rates in this framework.
M refers to the index M.
It's the nodes.
The nodes of the graph.
Yes, which node you are. Okay. All right, let me go with this, and perhaps this is going to clarify a bit more what is going on. So we start with bacteria. We are going to see how these guys move. We are going to be looking at how, I mean, E. coli, but a special strain, the enteromorphic, moves on a surface. So what happens with this is you have a glass surface. If bacterium is swimming, comes close to a surface, and then hydrodynamics is going to do 2 things. It's going to try to keep the bacterium close to that surface. And I mean, the hydrodynamics also is going to force them to move in circles. If they don't stop on the surface, then what you see is what you are going to see here. This is an experimental trajectory. And as you are seeing, the bacterium is moving in circles, it's noisy circles. So now what you can think is, if the bacterium tries to explore the surface, it's kind of getting trapped in these circular trajectories. However, this is not what we typically observe when you look at this to the enteromorphic E. coli. What you observe is that the bacterium performs some stops on the surface. And this is what happens in the experiment. You see that a kind of arc, suggesting that it's going to rotate like that, was stopped, and then another, right? Kind of another circular trajectory that gets interrupted, and so on. And you will see, and we will see it later, but I mean, the claim is that by performing these stops on the surface, the bacterium managed to explore in a much faster way the surface. Now, if something of interest was sitting on that surface, having a larger diffusion coefficient is an advantage for the bacterium, right? Because can quickly find, if it's a random search, what is performing, whatever of interest that may be on that surface, right? So having a higher diffusion coefficient is beneficial. So now I'm going to start looking at the data slowly, and we will construct the Markov chain. So as I said, the bacterium is performing these stops. You saw this here, right? So if I represent the velocity or the speed as function of time, what you can see is that the speed gets low values, then high values, low values, high values, right? So this is what you are seeing when the high values is moving. When it goes low, is that getting stopped, right? So there's noise, there's thermal noise, biological noise, all kind of noises here. So this is not flat. I mean, so you have fluctuations, But now if you look at the histogram of the speed, what you see is this bimodal, and now we can use this local minimum to define a threshold, and we are going to say that when it's below that vertical line is in the stop mode, and when it's above is in the run mode. Why we want to do that? Because we are interested in getting the statistics of this time, tau s and tau r. So the time that is moving and the time that is not moving. So this is represented here in is a survival curve, so cumulative. So this is time, this is that probability, and what you can see is that the distribution of run times is in a log-link representation, a straight line. Now, if you look at the blue ones, it's not a straight line. Okay, so let's assume that because we have observed just, we are talking about two different motor states moving at not moving, stop, then you may assume that you can describe this using two states, I move or I don't move. Problem is that if you think of this and you think of this like rates for S to M and from M to S, you would get for the blue one also a straight line, but this is not what we see experimentally. It's not a straight line. So if you're a Starman and you want to keep on using the Markov chain formalism, what can you do? Well, there is a simple answer to that. You enlarge your Markov chain. Now we have 3 states instead of having 2. If you allow me to use 3 states, I know that I can describe the red, but as well as the blue. Now, because the blue is not just a straight line, it's there where I know that I need at least 2. So now we have in principle, all transition rate between every of these states. And now the question is, we are postulating the existence of 2 of these states. However, this was by looking at this data, right? But we don't know, I mean, if we can identify them really from the data. So you know that in order to describe it mathematically, you need to use 3 states in the Markov chain, but what we don't know is how to interpret these 2. So this is, in order to do that, what we are going to do is to look again at the data. And this is what happens in the data. So what you can see here is we started to look at the events where the bacterium was stopping. Sometimes the bacterium stops and basically it performs no motion at all and then resume moving. And sometimes do what you can see here. When stops start, I don't know if you manage to see it, start to rotate around and then get detached from the surface. And that allows the bacterium to basically resume moving in some direction different from the one it was coming, right? So now we can define the states in the following way. I mean, when it's moving, we say that it's running. When it's in this state that is rotating, we say that it's in state 1. And when it's not moving at all, we say that it's in state 0. Okay, so now that we have these 3 states, what we can do is basically we can measure for how long it's in state 0. I mean, the distribution of times in state 0, in state 1, and in state 2. You can measure as well the average time you are in each of these states. And you can also measure how often, that is what you see here, how often you go from 0 to 1 and how often you go from 0 to 2, and the same for all states in the system. With all these measures that we take from the data, you can construct every transition rate in the Markov chain. Here, as you can see, I'm not putting 2 of these arrows. We measure and they are there. So, but the values were very, very small. So we take it with and without those. Here I'm showing you the version where I directly neglecting them because we obtain very small values for those.
Just
Yeah.
quick question. So you assume that the reverse rates are 0?
No, we measure every arrow in here. It turns out that those arrows were not present. We were getting tiny values for those.
But doesn't that automatically mean that?
No, we put it. I'm telling you, I mean, a shorter version because we are going to do some analysis. They were there. They were there. We measured them. We were as.
But then, I mean, okay, maybe I'm misunderstanding this, but there's no steady state. There's no equilibrium state. This is a
no, there is no equilibrium state.
Okay, that's
Okay. It was very nice mapping the stage to the phenomenon because you could see the moon, but what happens when you have physical system where you cannot identify? Is there a prescription to identify the state of the phenomenon, or was?
I mean, if you cannot get, I mean, a prototypical kind of pattern that you can identify, I suppose that you cannot go ahead with this procedure. So you need to do something with the data. I mean, if you cannot do anything with the data, yeah.
And first you use the framework of the Markov model then? You cannot distinguish these internal states from your data.
But I can, right?
In Markov models to infer that?
I mean, the Markov model, basically, the Markov model tell us what is the structure of this. And we did, I mean, yes, I need to identify to be able to measure it. Otherwise, I will have a certain level of, I mean, I have a problem. I could know or get an idea how should be this, I mean, this part with the blue ones, but I cannot uniquely identify the rates from the data, right? Because then there may be different numbers of rates that may give me the same output that I cannot. I mean, there is no, I cannot uniquely identify. What?
But you can make for most probable facts, right? Just the sign.
Sure. I mean, you can.
With a big number of hidden states, and then
sure.
Try to reconstruct the.
Yeah, I mean, here what you can do is see if you can identify them. If you identify, you make use of that. If you cannot, well, that's a different story. Yeah, I mean, it's not that the game is over. You can still try a few things, but I mean, if you identify,
you can observe it.
So the fact that you ended up with this model with 3 states, that was by being clever, right? It's not a data-driven approach. You have to look.
No,
at
it
data
is.
itself.
It is. I mean, how you? I mean, I started with 2. I cannot. I add 1 more. Now I can do. I stop there.
And you put some threshold of saying, no, I reproduce the data. No,
I mean, once you reproduce the data, I stop. I mean, you can put 20, and that is going to work as well. But then you can go with the kind of archaic criterion or different things, and you will just say, okay, I overfitting, so I won't do it. So I use the minimum.
Okay.
But
So you added a third one. But so if you're, so the reason you added this third one of this rotating, because you saw this happening in your data, you could have added something else.
no, it was not like that. In fact, I mean, it's a story. Yes, you're right. This is the way I told the story.
Yeah.
Well, I kind of told the story the way we look at that. I mean, we postulated the existence of that.
Yeah.
And if I went to measure that, in fact, was because I'm working, of course, with biologists, and they wanted to see it. Because in fact, before looking at the data, we figured it out by these other ways that you can, how would be this circuit. So we got that, and that was working, but was not satisfactory for the biologists I was working with. So they wanted to get a clear interpretation and visualization of each of these states. Then we went back to the data and see whether that was possible. And then we got this thing, and we thought, okay, this most probably this. We tested and it worked.
So you're saying that you first introduced the third state, then did you fit in without knowing what this third state
No,
was?
yes, we got the third state. We knew that there should be at least a
Yeah.
third state. Then what we did is we tried to describe the data with what we had. There was one that was easy to measure, that was the state, the rates associated with the running phase. And then we got a distribution, I mean, two exponentials. Now, if you look at that, then what you get is that the fitting of this, I mean, this curve that was there, that one, this one, there's almost, I mean, that was one way of fitting those with the degree of freedom that you were ended up having. So we fit it. I mean, we obtain it by looking directly at the data. I mean, in here, what I show you is that then we did something different. We went back to the data and we measured from the data each transition rates. The first approach was getting this and obtaining from this curve, not from this procedure. Here I measure directly. You do both and it turns out coinciding. I mean, pretty much the same numbers. You get the point?
Yeah, I get the point. Yeah.
So, yeah.
I wondered, like, if you go back to the slide where you have the red and the blue curve.
Yes.
Here, it seems very much that you have three typical time scales because the red is one exponential decay, and then the blue one has two different time scales coming at it. So from that, you already sort of match those Markov.
Exactly. You can do
race to get those time scales.
Yeah, you can. I mean, this is not a pure one. Basically, what you have, one gets a pure and the other gets a combination of the two. But basically, you get the Markov chain, you solve it, and you get an expression for how it is the outcome of times that you are going to be in these blue states. With that, you try to fit that and you discard some of the rates and you get that having what is the expression.
The blue one seems to have a separation of the
yes.
There's a late time slow decay and there's a early time fast decay.
So to check my understanding, if you would both add a third line to this plot with the rotating times, then you would end up with 3 straight lines. Because
yes, I mean, you can see in here that by in here what you get is 3 lines, and these are the ones, and that's why all work. Yes. Okay, so that was the Markov chain, but this was halfway from getting what I'm planning to do. So because from from this, what we want to do is what is happening? Okay. So what we want to do is to fit what came out from the Markov chain in an equation of motion, right? So the idea was associated in whatever was happening in this mini brain or in Markov chain with an equation of motion. Here is our equation of motion. The equation of motion is different as we get the internal state with this here, not Q, sorry, is I of t. So this I can adopt 3 values, 0, 1, or 2. So depending on what is 0, 1, or 2, this is going to modify these 2 equations. These are a Langevan equation. So the first one tells you how the bacterium, the center of mass of the bacteria is doing. So it's the velocity of the center of mass. And this one, you can think of it like the orientation of the bacterium. So this is in which direction the velocity of the bacterium and in which direction the bacterium is heading. So now with these 2 equations, as you move Q, you are modifying the equation, right? Suppose if I'm in state 0, this is not there, you are not rotating and so on. In the other cases, you may be rotating, but you are not moving the center of mass and so on. So I'm modifying what is my equation, and that is given by the Markov chain. So now, as I was saying at the beginning, you can describe still what is happening. I mean, of course, you can put it in the computer. This is what, of course, we also did. And you look at you do perform numerical experiment and you obtain your diffusion coefficient, whatever you want from the HM-based simulation. But you can also get the probability of finding your particle or unit in position X, moving with orientation theta at time t. And then what you can do is the following. You can write the equation associated to this. Is in this case is this one. You write down those equations, and now what you can do is what I was telling you before. You can try to get the effective diffusion coefficient out of this set of equations. This is this one. So this effective diffusion coefficient has the following. Depends on how we wire the Markov chain, and of course also on the rates that we use in this circuit, right? In the Markov chain. So now let me show you the following. So this is the diffusion coefficient as function of one of them. So this is K20. K20 is the one that controls for how long the bacterium is moving. So now what you can see is that there are two limiting cases that we can easily identify. One is when the K20 is very small. Basically, you get locked in the running state, that is, you don't perform any stop on the surface. Then you get this diffusion coefficient. So since you are basically staying in the same position, your diffusion coefficient is not very large. You are around here. And the other is when the K20 is very large, which means whenever you go to the red state moving, you immediately go out. So that means that you basically stay in the blue nodes, basically you don't move. So the diffusion coefficient is very low. So, and as you see, there is a K20 that maximizes the diffusion coefficient. And I was trying to tell you that you can argue that should be, beneficial for a bacterium because it's the way of exploring a more efficient way the surface if it's performing a random search. And the good thing is that these guys operate at the maximum that maximizes the diffusion coefficient. Now you can do the same procedure with other bacteria. I mean, the different, from not E. coli, but different strain of E. coli and different bacteria that also are peritrichous and also perform these stops. And you will find that in general, they stop at the frequency. The frequency of stops is that optimize the diffusion coefficient according to the calculation I show you. So it seems we check it in different other bacteria, and that seems to be working.
Does this peak in the diffusion coefficient depends also like on the environment, on the medium that they are in?
Yeah, of course, that depends. Here in this experiment is as homogeneous as possible. So if you want biological, you can argue how realistic or interesting is for, is guys on moving on a glass surface. So we did other experiments where we use a PT model to see how they infect cells that are sitting on a surface. But this is a different story. I'm not talking about that. But there things are different because then you may have or not. Most probably you have chemical gradients, so information about where things are located. The bacterium should react to that, and the story is slightly different. These experiments are they have no, there's nothing. It's the glass and the liquids.
Is it different bacterial species depending on the habitat?
Of course, you change the environment, the reaction of the bacterium is going to be different. The maximum, these kind of things you will see if you perform experiment also on glass and different species. Mm-hmm. So then if they, we can go more into the details, but of course this depends on whether the bacterium, for example, if perform stops get adhered to the surface, I cannot detach. Most probably it's not a very good idea to perform any stop. Yeah. So, and then if it's not being able to adhere as to perform this rotation and there to break the circular trajectories, is probably also not a very good idea to do it. So then you have, a range of, properties of the relation between the adhesion of the bacterium and properties of the surface where probably, it's a good idea to perform stop on the surface. When if you observe stop on the surface of the bacterium, for the ones that we check it, that other groups were measuring things, and we went there, so they tend to operate at the value that maximizes the diffusion coefficient. Okay, so
an observation is that at very low K20, there's still quite a bit of diffusion, right? So, and you said that it's in a circular mode, but it's apparently still exploring the space.
Yes, because it's a noisy one.
It's right? Noisy, so it moves around.
Yes, it's a circle that is doing like that and moving around. Okay, so basically from this part, which is already quite a okay, so bacteria explore. This message is exploring the surface by performing transient stops on the surface. and I show you that it's a maximum, I mean, an optimal stop frequency that maximizes the diffusion coefficient. Okay, now I move to sheep and I will use basically the same approach. So, yeah.
It's very that exactly at the peak of the diffusion that the bacteria, the radiation rate is. But do you know why? How bacteria know to optimize so well the ional mass?
I mean, we know that they have a lot of different mechanisms in order to regulate that, and there was measurements about how they perform the stops. So yes, they could sense in which surface they are moving. So how is the entire machinery inside to regulate that? I don't know. But if they can sense which kind of surface they are. So that is pretty well known. And also they will need to understand whether they are, for example, on a cellular tissue, where they're on glass. And I mean, they need, otherwise they will get stuck wherever they are moving, or they will simply slip and move away from areas where are of interest. So there is a lot of things, and there is a lot of mechanical sensing of the environment. And there is a lot of things going on inside the bacterium, which is very complex, all that. So
Could you change the kind of surface? So you
I mean,
matrix.
we have not, but other people have done. You can do, I mean, you can treat it in such a way that they cannot adhere. So this is, even if they could sense and try, I mean, now the adhesion of the bacterium will not work, and they will keep on, I mean, then you will get it in cellular trajectories. I mean, you treated the surface in such a way they cannot adhere, in such a way that all this is not going to be there, of course. And of course, you can also do the opposite, and also we play with that. You can, I mean, if not on the surface, but let's say you put something that is extremely sticky, the bacterium comes, and that's it. I mean, once getting there, cannot detach. Of course, if you go to those limits, everything that I said is gone, because the bacterium in one case cannot stop, and in the other it never been able to basically to escape from once they got on that surface, right? Okay, but then you have how it's going to move when you have a bacterium, let's say in the gastrointestinal tract, or situations that may be of biological relevance. That was a question. No?
Just I have a very quick question. Was it the single strain of bacteria experiment, right? Like you can have multiple strain, and then you can see how they compete and how they.
Yes, this is what I said. Yes, competing and so on, we have not tested, but we were looking to the enteromorphic. There's other people that were looking, I mean, to the ones basically that, so they have a strain of E. coli that are particularly good at doing different things. These ones are very good, the ones that we study, in affecting the gastrointestinal tract and produce bloody diarrhea. That's why the name. So this is it's a quite pathogenic and dangerous E. coli. Then you have the others that infect the urethra, and that means this different, let's say, two area where they are very efficient at stopping and infecting and getting basically colonizing. So then they were doing experiment with this one. So the frequency of stops slightly different. Adhesion properties are also different of this strain. So different adhesion properties, different frequency, and so on.
Because I can imagine if you have a population of different strains, so they cannot all optimize their maximal diffusion, right?
Yeah, but yes, of course, that's true. Now the question was connected how adapted is the behavior. And now there is experiment that suggests that they can adapt their behavior.
So they can change the peak of the distribution.
Yes, I mean, basically that's the things will get modified as they sense the environment. Also, you can go into looking at the problem from more evolutionary perspective, right? I mean, but it seems that they are able to adjust, really.
Is that just adjusting the rates, or could they get new states in the market chain?
I mean, How they do it actually, bacteria, I mean, I don't know. I mean, what we know is that in principle they can sense and they can, I mean, the entire machinery, they modify, I mean, you have a bacterium that is performing, let's say, tumbling events at a given frequency, you change the environment and that modifies the tumbling frequency.
I have a question. So we have this nose, it explains the behavior on this glass. Does it correspond to anything biological inequality, this nose?
I mean, yes, I would say, because I mean, one is moving, the other is not moving at all, and the other is moving at the air on the surface. So they have a clear interpretation for each of them, right?
Yeah, but when we plug in these equations, we like use these equations one by one, and we like go to the biology of ecology and seeing what is active there. Like, is this nose representing something biological abstractly?
I mean, but I think this is this is one of the nodes, the red one is moving. So when you see this. Well, at the beginning it was in state 2. Now it's in state 1. Now it's back in state 2, right? So there is a clear interpretation of what is happening. And what I'm not putting in this figure is 0. 0 is when you see the guy moving and then stops and then continue moving.
It's now in state 0.
What?
It's currently in state 0.
Yes, now it's currently in state 0 but it's because the film stopped. And the movie, the video, right?
Is there any relation with chemotaxis? Because there was the question of why this happened.
I mean,
gradients of.
This is something that I'm not talking now, but I mean, in fact, what we know when we put the cells that can infect is that close to the surface they cannot do chemotaxis. So yes, they can do whenever they come swimming. Once they get to the surface, the data indicates that there is no chemotaxis. If you read literature in from biologists, they assume that there is chemotaxis, but we don't get from the data any bias towards these cells. So there is no chemotaxis going on when they are on the surface. And the reason for that, I mean, one possible explanation may be that they need to disassemble, they have a flagellar bundle and they have to open it. And perhaps it's the physical constraint on the surface that prevent them to open it. So they are very inefficient at doing this change in the direction, or they're less efficient than when they are in the bulk. So at least the experiments we were looking at, I mean, there is no chemotaxis going on. Yeah, even when you have cells that they want to infect on that surface, right? So, but this is a different story. So let me tell you a bit of sheet. I wanted to tell you a bit of sheet. So now we will use exactly the same framework to look at sheet. Before going to that, I don't know how many of you know about the big sheet model and so on. So let me give you a short reminder. I mean, this is the standard way of looking at a flock. Is you have, let's say, birds, fish, whatever thing moving in the same direction. So how can you explain this kind of phenomenon? Typically, a standard way of looking at that is to say, suppose this is your focal particle, is the red one. What does is measure the velocity of the neighbors, and what does the particle is align its own velocity with the velocity of the neighbor. So and everybody end up moving in the same direction. The group is constantly on the move. I mean, this is the observation is constantly on the move and constantly negotiating with the others in which direction to move. There is no leader, and the information they exchange is the velocity of the neighbors, and that allow them to do things like information pooling and so on. And the group moves in the same direction. So basically what I'm going to show you now is that the data I managed to look at here is going to be for sheep, but well, for the sheep data, you will see that nothing of this works. So the typical picture is not working. And I have strong suspicion that probably that applies to a large number of biological systems. Because if you think about this kind of models were basically proposed before we got any access to data. So we saw how we consider how things should work before looking at the data. Now the data is there, and we tend to interpret things, assume that should work the way we initially thought that should work, right? So that goes into more philosophical discussion. So now I show you the data. So you will have look at 4 individuals. These guys, what I want to show you is how they move. So they are there. So this is they enter by this part. So as you can see, they stop, they move. When they move, they're moving fine. So they are eating there, they move in that direction, they stop again, and you will see them coming in this direction. Here they are very close to this fence, and they are close to this. There's a tower here from which the pictures are taken. And if you wait a bit, you will see them coming towards us. And you will see that they move one behind each other, right? So let's look a bit more to the tracking data. So this is experiments. So here is a group, again, not moving. And now you will see a collective motion phase. So here is the red individual. I mean, the individuals, the color it tells you is the label of the individual. Now was the purple one leading the group. And then this will keep on. I mean, you will see that someone else, now I don't remember which is the one that is going to move the group in this direction. I'm going to yellow one. Then you will see another collective motion phase. Now is the blue one, and so on, right? And as you can see, so the group stops and moves, and when they move in file formation. So again, so this is the kind of scheme. So you have racing phases. I mean, phases where the group is not moving are these gray, GP1, GP2, and so on. So they have the collective motion phases when they decide to move. And as you can see, they move kind of line formation. And every time that there is a collective motion, there is someone different that is in front of the group. So with this, I go again. This is from what the typical way of looking at collective motion is that the question is how they agree in which direction to move. And the assumption is that the group is moving constantly. There is no leader and so on, what I mentioned before. But here what you are seeing is something different. And we will consider that is that basically the group, the collective motion is an intermittent phenomenon where the group stops and moves. You will see that they're temporal leaders. We will define what is that. So individuals that are at the front and others that are following. And that means also that the direction of motion may be decided at the moment one individual leaves the group or start guiding the group in one particular direction. And I will show you at the end that what they change is positional information and not velocity information. Okay, so with this, I start with the first question, that is, we start from a group of static individuals, and we see that one individual start moving. So this one and that one trigger a collective response in the group. So everybody started moving. So at the moment, I'm going to go back to the picture of the bacterium. This is for individual number 1. This is speed, a function of time. So as you can see, the individual is moving, not moving, moving, not moving. Now, if you look at the distribution of speed, looks this way. You take again a threshold and you define, you transform this signal into a binary signal for when it's, I mean, this in fact is a 1, that is when it's high here, it means that it's moving, and when it's low, it means that it's not moving. And what we are interested in is understanding what is the distribution of times the bacterium is in the moving state and in the non-moving state. We want to do, to look at the statistics of this. This is what you see here. This is the statistic of stop times, which is this kind of shape. So it's kind of gamma shape, and the distribution of run times. And again, we have the distribution of run times. This time is lean or representation. And you can see that the distribution of runtime is also an exponential, but the distribution of stop time is not. So if I go again with the same question, can I use two states? I will get an exponential for both of them. As you can see, this is not an exponential, so not a good idea to use, at least if we want to reproduce the data, to use two states. So what is the solution? We enlarge the Markov chain for 3. If we have 3, you can also explain a gamma shape, no problem. So as the two exponential, you can also get this one in this kind of shape. This is the red curve in here. So that can be done. So again, we know that we need to postulate the existence of at least two states. Another question is, what are those states? So for sheep, these are the following state, how we associate it. So S1 is when the sheep is not moving head down. S2 is when it's static head up, which we will associate with another state, and M means that it's just running. So again, you can measure the time is in each of these states, and you can basically compute from the data how often go from S1 to S2, S1 to M, and so on. So you do that, and you get a perfect Markov chain, you get all rates, and if you get that, you get basically you can understand what happened with sheep 1 without no problem. We got it from the data, so we reproduce all the statistics without any problem. Now, here I'm looking at the group, not only at sheep 1. And the problem here is that whatever is doing sheep 1 is almost the same that sheep 2, 3, and 4 is doing. So the the new challenge here is that they are not independent, as you can see here. So what is happening here is that there is this thing that I see on the screen anyway. So they exhibit a very synchronized behavior, right? So how can you describe that? And so this is the idea. The idea is that we need to include in the description some kind of imitation and how this can be described mathematically. But before going into how you do it, how you, can mathematically describe imitation, you can measure and make clear evidence, experimental evidence of this imitation behavior. So how was done this? So you can train this individual in order to do the following. This individual has a collar. That collar you can activate remotely and will start vibrating. When it starts vibrating, this individual will know that need to look for a yellow panel. And it's going to do that because when it comes to the yellow panel, it's going to receive a reward. So once it starts associating this, the collar vibrates, a yellow panel will show up. Close to that yellow panel is going to receive a reward, and then it's going to run towards that position. So why we want to do that? First, we want to do that in order to show that if we manage to control one guy, we will control the entire group up to a certain size of groups. And that means that the intention is we make this guy move, then some others will follow. And the question we are asking ourselves is what probability an individual that is static decides to join the group that is moving or stays with the ones that are not moving. Okay, so here is the experiment. So you will see the tracking around here, the trained individuals around this part. You will see quickly coming, I think, now. So the individual is over there. It's the blue one here, and all the ones are following. Okay, so you can see that you can repeat over and over. Of course, you will need to change the group to avoid this. That the response is the same, but basically this is quite reproducible. And well, you can put in evidence that they imitate each other. And from this kind of experiments, what we obtain is how is the transition rate. The transition rate depends on the target state you want to go. This is this final, and depends on how many are in that state, how many individuals, neighbors are in that state, and how many individuals are in the state you are at T0, let's say. And so the ones that are in the final state are going to stimulate you. I mean, the transition rate increases in a nonlinear way with how many are in the state, I mean, in the target state. And the ones that are in your own state produce any kind of inhibition effect. The more are in the same state you are, less prone you are to perform a transition. Okay. So now when it comes to the data, I show you there was no trained individual. These experiments were done, I mean, to put in evidence what is the transition rate. Here what we have is the problem that everybody is, for example, here in a moving state, or could be in a non-moving state, and a transition occurs. So what we need to understand is how is this spontaneous transition rates, right? So this spontaneous transition rates is the only thing that remains to be understood here, is what I show you here. This was done by changing the group size. And basically, now if everybody is static, and there is one individual that does the transition, this is for a group of 3, 4, and 8, and these 2, 3, and 4, what I'm showing, the experiment were 2, 3, 4, and 8 and 16, but the tracking was not that good. I mean, that was why we didn't put it. Anyway, so what we ended up having is that the spontaneous transition rate is not just spontaneous as such, because you have to include the inhibition of how many are in your own state. And in fact, though this is coming from the data, that is possible to, I mean, conclude that has to be the case, because otherwise, the more you have, the larger is the group, the more prone is to perform a transition. And that means that the group would get kind of excited, accelerated, the more individuals they have, right? You understand? So for example, I'm a static group and I have 100 individuals. Now it's going to very quickly transition to a moving state. So this is clearly something that you don't want. You want the group to stay a bit in, I mean, not moving, because this is what allows the individuals to basically get food, eat. So it's the grazing phase. So in order to do that, what you have to do is basically, you have to, the more you have, less prone should be per individual, the transition rate to transition to moving state. Hope that you understand what I'm trying to say. All right. So this is another measurement that we performed. We measure how often the individuals in our experiment were acting as a leader, and we found that this was consistent with the binomial distribution, indicating that everybody has the same probability of acting as a leader. This is also the case because we use groups of females of 1 year and a half, so same sex, same age. So if you change that, this is not going to be true. Okay. So now what you have is with this, what you do is you feed again an equation. This is a very, very simplified one. So I will show you what happens if you just project everything in 1D. Basically, they move or they don't move. And then what you can do is basically, these are the experiments. Head down, head up. So, and they are moving. So this is a 1D representation. And this is what you get from the model. And basically you get something pretty much the same. So also, I mean, kind of synchronized behavior. When they move together. And this is how the things evolve.
Yeah.
Okay, so.
Right, it looks very natural.
Okay, and with that, I mean, there is a bit of math that you can do with here. That is, I mean, the groups were small, right? But if you enlarge the number of n and you extrapolate what should happen, you can prove, you can basically map the problem to a problem that looks this way. That basically what you can show is that the system behaves in a way where you have three fixed points that are stable, three fixed points that are unstable, and at the end, the entire group is behaving like a kind of a stochastic social oscillator where it stops, moves, and so on. So
activity which is position.
this is the position you are in these phases. It's in the phases of how many individuals are in the running phase, how many individuals. So it's a representation to saying it's in behavior state. Yes. Okay, with this, there is something that, comes out also from the experiment, which personally I found it interesting, which is the following. This gives you also a hint why many individuals want to be in groups, at least like ungulates. These guys, basically, if they are alone, they can choose what they want to eat. And they can, this guy can go and pick up whatever he wants. If there are others around, there's, of course, competition. So you could say, without putting any other constraint, might be good to be alone and not with others. However, if you are alone, also you are alone to look for predators, and that means that you will have to spend a long time looking for predators. So basically, now when you look at the data, what you get is that the time that the individuals are static with the head up, that now we are going to interpret as an alert state, decreases as you increase the group size. From 2 to 8, you see that goes down the time each individual spent with the head up, the average time. Now, if you look at the group remains always the same. If you look at the group and you ask when there is at least one individual with the head up, that remains basically constant with the group sizes. So that means in a group of 8, one individual will spend less time in an alert state, but the level of, checking for predators is the same, right? So by being with the others, you spend less time in an alert state, so you can devote more time to eat or doing whatever else. So that gives you an advantage to be in a group. Till when you want me to continue? Should I continue or stop? Okay.
State can be seen in risk avoidance. So this is
Okay, so
is it related to risk avoidance? Like then why you decide to be in a group, or
this one tells you when basically the advantage of being a group. So what there is there that I'm not talking about here is that also you can define up to some point it's no longer good to be, the competitions becomes relevant, kick off somehow, and it becomes so important that you don't want to be in the group, and the group will be split. So there is a complicated dynamics with the group size. I don't know if I was clear. So this is for group up to 16, but at some point you can also see that, if you put some other constraints, suppose put a variability at some point, if we put, well, we have not done properly the experiment, but if you put food patches, small ones, suppose that only 8 or 5 could eat, of course, at some point, even though you may look for predators, spend more time eating, whatever, but if there is nothing to eat at some point, it's no longer convenient, right? So you can force group splitting by trying to limit the availability to resources. Okay, so with this part, basically now what I will show you is the kind of information they can exchange when they are traveling. And this is the evidence that there is, a leader, the one that is at the front, and what information, what we want to see is how information is, what information is being exchanged as they are moving, and what information is being exchanged and how. So basically, this was the data I was showing you before. So when they were, let's say, I think now it's the red one that goes in front. And basically, we want to see how that happens. Well, basically, if you see here, what we want to see is how they move in file formation. And okay, so what we did is we assumed that all these options were possible for them. That means this stands for interaction network 1, 2, 3. We play with a couple of others as well. And basically, here means that everybody may influence all the others as they are moving together. And in the other extreme, we have this one where basically I'm seeing the individual that is in front and reacting to whatever is doing the individual that is in front of me, and I'm ignoring everybody that is the back, right? So that is this one. So now how we measure that? We measure how was the velocity correlation between two individuals. So you get individual I, individual J, and basically we try to see how is that correlation. Basically, if I know the fluctuations in velocity of individual I, can I predict what is going to be individual J some later time? Or if I exchange, I can predict what is happening with the other, right? So the first, something that quickly one can see is that the interactions are non-reciprocal. They are very, very different. They are never, if knowledge on individual, let's say 1 is going, you may get what happens with individual 2 later time, but if this is happening, the other way is not true. So basically, 1 is influence 2, 2 is not influence 1. That can be very clear from the correlation between any pair that you look at. And then if you look at these options, I will give you few reasons why at the end we will pick up this. But basically, the goodness of the fit that you getting this one is almost identical to this one. Then if you use one criterion, here you have the number of parameters is larger and the fitness is basically the same. So basically you will discard this. But then I will show you another reason why you can discard this one. Okay, so that means that we will pick up this one, interaction network 3. Now, there's 2 things that they can exchange or that we consider. One is that they look at what is the velocity of the neighbors, and the other is they look at the position of the neighbors. And here, these are the equations, but let me show you what happens. If what they do is they look at the velocity of the neighbors, the problem is that when they start interacting, they cannot form a file, right? To form a file, you have to take into account where the others are located. And this is what is happening when they exchange positional information. With positional information, they will manage to form a file. And as you can see, they can also be pointing in the same direction. So the fixed point for this system has 2 things. So individuals have to be in line. And to be in line, that means the velocity of everybody is the same. So you get velocity is the same. So it's parallel to each other. And you do that just by using positional information, not velocity, right? So for velocity, you cannot form a file. So that gives you already a very good hint that what is happening is that you use interaction network 3, and what you are exchanging is positional information. So this is what we end up having. And if you are interested in this difference between velocity exchange or positional exchange, we have written a paper with a vision cone and so on in 2016 about that.
Can it be that they use more information?
Yes, you can use that. And then you incur into overfitting. There is, yes. You add it and you get again a good description of the system. But if you remove velocity, you get exactly the same level of the goodness of the fit remains the same, but you are using number of parameters that is way less. Then you can use this archaic criterion or other criterion to decide which model you should use, and you will discard the other one because you can basically argue that you are incurring into overfitting.
I guess, like you said, if you have the trajectory in time, then you have those automatic.
Yes, I mean, this, but let's say for free, by following another one, you will align the velocity. That's why it becomes redundant to use the other one. So, and this is basically what you get is we get the individual up front, and this is basically what gets from the model. You get that very good description of, I mean, you can predict where the others are going to be and what the trajectory is going to be. Basically, they are going to follow the leader. So this is what is telling you this figure. And if you exchange something else as velocity, or the prediction is not that good, and so on. So with this, I will come to the end soon. This is the following. Suppose I said to you that you can assume why you should use interaction network 3 instead of interaction network 2 or 3. And this is the example. Suppose if they are moving around here and you exchange which kind of interaction network they are using, or you exchange, I mean, you start exchanging velocity information instead of position information, what you will see is that suppose the individual at the front here knows the way through the maze. This is just theoretical experiment, right? This is not the experiment that we want to do. So this guy is going to find the exit because has a prescribed direction where it has to go, but will not manage to guide the rest. But if they do it with interaction network 3 and position, this is possible. So this guy will be able to guide the group. So now why, if these guys tries, let me go again. If this guy in here tries to basically pay attention to what is doing this other guy in here, so there is a problem. I mean, it should ignore, has to trust in his own knowledge and ignore whatever others are saying, right? So it's very hierarchical. So only that way you will guide it through the maze. If not, if the guy starts to thinking, okay, I'm not turning this, but my friend is still moving ahead, and I try to get a compromise of in which direction I want to go with the one of my neighbor, I will end up being not taking the correct direction, right?
I mean, if you throw in more sheep, there's this one way.
Sorry?
You throw in more sheep, so it becomes more of a herd, and you throw in the sheepdog. Does this one-way communication break down?
If you, I mean, we were trying to do experiment with dogs. We have some data now. I mean, with dogs, what happens is that very often the individual that is at the front will get scared if the dog comes and will look at trying to get with the other group members. So,
and still this one-way communication, still, because I would imagine that there's many sheep that react to the dog, and then it's more of a collective kind of feedback that happens.
Yes, I mean, you may break this file formation when the presence of the dog, because everybody may get scared. But now comes something different. If the dog is present, typically what they try to do is they try to hide inside the group. And so very often what you end up having is a vortex, which I found surprising. So the sheep start turning around because nobody wants to be the leader, right? So they follow each other and they start turning in circles. And what the dogs do, which I will also found incredible, is they manage to jump on the sheep. So literally, and they break this vortex by getting in the middle. So they go to the topological defect that.
The penguins have the same thing with the vortex, I think, when they protect each other.
Yeah, but could easily be that they do that. All right. So with this, yes, you have a question.
Very nice second part, but you mentioned in the beginning this zigzag model, and then for the beginner answer, the only thing I knew about this collective motion. Would you make a pitch like the main difference between your approach and the zigzag? What exactly capture your node and vice versa, what's the
Yes.
distance between each?
I mean, the Vic model, what they do is they basically you interact with the velocity of the neighbor, right? So what I'm telling you is ignore I mean, we don't care about the velocity of the neighbor. What you care about is the position of the neighbors. Second thing that you need in order to produce this collective effect is non-reciprocity. So because if basically this is attraction with breaking Newton's third law. Because if I have a vision cone or I have an interaction network that is hierarchical, I see one individual, but I mean, the arrow goes in one. You don't have two arrows, but only one. In that case, you would get a flow of you create flows, and now you can get floats and so on. So you get this has basically nothing to do. On top of that, I'm considering that the group is stopping and moving, and the picture they are constantly on the move. So there is no stop. I mean, the group doesn't stop and move; it's constantly on the move. But I'm telling you that if you get attraction and you plus non-reciprocity, I mean, you break action and reaction, Newton's third law, then what you get is flux, and they can move in one direction. So very, yes, very different, right?
Yeah.
It's in the other is isotropic in the big shape, and you pay attention to the velocity of the neighbors. Here is the position, and non-reciprocity is absolutely key, because otherwise what you would get is just aggregation, and you don't want aggregation. You want things that move in one particular direction, and in order to do that, you have to create a flow. I mean, if non-reciprocal interaction, that is going to happen. Okay, so with that, the other thing I wanted to say is that this intermittent kind of behavior, what allows them to do is over time, I mean, this was this idea whether if everybody has some idea where a target is located, let's say a food patch, whether they can exchange information to better locate that food patch. So in the Viction model that or Cousin model, that is possible. So they can basically do what is usually called information pooling. And here they also can do that by the fact that they change who is the leader over time. So over many sequence of changing who is the leader, they can also do information pooling. So basically, I think well, you can say SHIP has invented democracy in the sense that they have an individual at the front over a period of time. They change who is the one that is going to lead and so on, and so on. So and that increased the accuracy with the group size, right? And yes, probably this this is related with the wisdom of the crowd or collective intelligence, the problem of Galton of getting the weight of. There was a group of people and they have to guess what is the weight of an animal. And basically, if you get the guesses of many, you get a very good hint of what is the weight of the animal, right? So here you can do basically the same. The more you have, the better, more accurate is the navigation. So with that, what I show you is that the ship, what they do is with this intermittent collective motion, they do they take advantages of hierarchical strategies, meaning you can use, if someone knows the solution for a maze, you can make use of that and guide the group through the maze. And they can also perform information pooling. So we take advantages of also kind of democratic strategies. And that's again a difference with the kind of Viction model or this other way of looking at where is just a purely democratic strategy. This is alternating between a hierarchical strategy and a democratic one, and that has advantages. I mean, now you can. That depends, the circumstances. It could be convenient for you to have just make use of hierarchical strategies, but also you need at the different kind of problem-solving kind of situations use democratic strategies. So Also, you can see that 5 formation, and then you can go enlarge the group size, and you get this kind of things. So this also happens when it's not 4 or 16, but many more. And with that, I was going to go, I think this is super late, but another part that is something that we have been doing recently, that is how you get propagating waves in this group. That is how one start moving and how this propagates over the entire group. And whether, I mean, you can see that in 1D and abstracting the model, this model can be mapped into this model with 2 states, and active can be mapped to the SIR model on a lattice. So basically, it's possible to map mathematically a 2-state, an active 2-state, to a 3-state static standard model. And with that, let me go with at least the conclusions I wanted to show you, which is this. How would I convince you that? I mean, basically, what I show you is we treated bacteria and sheep more or less in the same way. What we started is by looking at the speed in these 2 cases. We converted the signal into a binary signal. We look at how long was in each of these 2 states. We use that to construct the mini brain. We plug that mini brain to an equation of motion for how things move in space. And by doing this, we managed to explain what was happening with bacteria and sheep. Okay, and with that, I thank you. And these are all the guys that work with me to do the things I showed you. So it's Luis, Adrian, Silvan, Richard is as the biologist doing that. Parisa was in the last one I couldn't show you, and the sheep, of course. Okay, thank you.
Just a quick question out of curiosity. What happens if there are 2 leaders at the same time? Do they compete?
We don't know. That was plan of, I mean, in the model you can do that, and in the model what you are going to see is that it depends who you can lead. I mean, that can lead to group splitting. Also, the one that reacts the first typically is the one that collects more. Now it depends what rule you put to the other leader, if it's going to completely ignore the others. I mean, the other leader, or is going to be influenced by. So there were like modeling choices. So we don't have a unique answer to that. And we wanted to do experiments basically with 2 leaders and see what happened. I mean, we have not done it yet, or at least there was an attempt by some years ago by Silvan. I think the group, they were either not reacting. I don't remember the details, but it was not few. I mean, the ideal situation is to say now, and both of them started going, right? And that was very difficult to do.
So going back to your first slide, so when you made this, you don't have to show it, but originally you showed this kind of 3 phases of motion, and it was mapping to this Markov chain. In principle, these phases of motion could be multiple Markov states. Now, in the bacteria case, it was just a 1-to-1 mapping. So there was 1 state to 1 phase of motion. The sheep was a bit less clear to me because it's the head up thing. And then I wondered, is it then just another analogy to traditional state-space models of movement ecology where you can
which kind of model?
Just state-space models. So I think Dan mentioned the hidden Markov models that you use to extract them. So does it become completely the same then?
No, yeah. I mean, there is of course an overlap in the way of thinking when you're coming into the Markov chain.
Yeah.
In the interpretation of the data, I think it's that comes something slightly different, right? Because now it's whether this. If you assume that you don't have access to that, and also is how you plan to construct your hidden Markov chain, if you assume that there is one, right? I mean, there is one in the way I'm looking at the problem, is assuming that you have, in principle, an n a Markov chain with n states or n nodes. And now we want to see what is that n and how they are wired. So yes, but now is what we have used in order to do that, right? I mean, that was very specific into moving, not moving, and basically to trying to understand how these guys switch from moving to not moving.
Yeah, the sheep one made this clear.
Yeah.
Nice talk, thanks. Coming back to this comparison of VICSEC and your model, because you mentioned in the beginning that you could have many microscopic models with the same macro behavior. And you showed several setups, and it's known that the VICSEC model used to flocking. But I don't know about other types of behavior. Do you have an example where one model uses different
I mean, the one I show you, I mean, this one.
the labyrinth stuff?
No, I mean, which direction I'm going? If you look at, where did I put that reference? Here, I think. So that paper there, I mean, we show also okay, you have the Vickers model. With the Vickers model, you can get these Tonner two equations, right? So if you constrain and you go into, if you try to get the sort of whatever universality class or a long range order is possible in 2 dimensions there and so on, you can use the Tonner two approach, which is the phenomenological one, right? So now you try to go, if you try to constrain, really not going to a phenomenological constraint level, but do the process of getting from a microscopic description to a macroscopic description, you're going to end up with something similar to the Tonner two equations, where the coefficients are going to depend on the density and other quantities. Okay, so now if you do the same with that model, with the position and so on, the set of equations that you end up having is very different. So they belong to a different class. Right. I hope answers to your question. This is the only example I know where the entire process has been done. In that case, the phenomenology that we see is different, but the macroscopic equation is also different. So they are living different universality classes, if we can talk about universality classes. Yeah.
They're not,
No, they are not the same, not at all.
Has a question? Okay.